Picture this. You are standing on the deck of a ship longer than 3 football fields. Below you, more than 500,000 tons of crude oil are sitting in the belly of this steel giant. Above you, the sky has turned the color of a bruise. The wind is screaming at 100 kilometers per hour, and the waves are not waves anymore. They are moving walls of water, some of them taller than a 5-story building, and they are slamming into the hull of this ship one after another. Now here is the question that should terrify you. This ship weighs more than 500,000 tons. It is taller than most buildings you have ever walked into. And the ocean at this exact moment is doing everything in its power to flip it upside down, so why doesn't it? Why does a piece of steel that would sink in your bathtub in under a second manage to survive conditions that would tear a smaller vessel completely apart? Why do these floating cities of metal ride out storms that make news headlines, while the ship itself barely makes the crew spill their coffee? I am going to tell you right now, it is not luck. It is not some miracle of modern shipbuilding that nobody can explain. It is physics, cold, calculated, terrifyingly precise physics that engineers have been perfecting for over 2 centuries. And once you understand how it actually works, you'll never look at a ship the same way again. By the end of this video, you are going to understand exactly what keeps a 6,000-ton tanker upright in a hurricane, what happens inside that hull when the ocean tries to kill it, and why, even with all of this brilliant engineering, the sea still occasionally wins, because it has, and when it does not go well for anyone on board. Let's get into it. Here's a question for you before we go any further. If I handed you a block of solid steel and asked you to throw it in a swimming pool, what happens? It sinks instantly. No hesitation. Every single person watching this video already knows that steel does not float. You learned that as a kid throwing coins in a fountain, except steel is way heavier than a coin. So here is the actual mystery we need to solve today. If steel sinks always, every time, no exceptions, how does a ship made entirely out of steel, carrying more steel in cargo, weighing more than the entire population of a small city, manage to sit on top of the ocean instead of underneath it? And more importantly, once it's floating there, why doesn't a massive storm just tip the whole thing over like a bathtub toy? Let's go back about 250 years, because this story does not start with modern engineers in some fancy office with computer simulations. It starts with a very stubborn man and a very expensive bet. In 1787, there was an English industrialist named John Wilkinson. Wilkinson was obsessed with iron. He believed iron was the future of everything: bridges, buildings, machines. And one day, he made a claim to his colleagues that sounded frankly insane for the time. He said he could build a boat entirely out of iron, and it would float. His friends laughed at him, and then they bet against him real money. Because everybody in that room had watched iron sink. Everybody had thrown a piece of scrap metal into a river and watched it disappear straight to the bottom. The idea of an iron boat floating was, to them, about as believable as a boat made of bricks. Wilkinson built his barge anyway, 21 meters long, welded together from iron plates, flat-bottomed. And on the day it launched into the River Severn, a crowd gathered to watch what they assumed would be a very expensive and very embarrassing disaster. The barge floated. Not just floated, it floated exactly as Wilkinson had calculated it would. His friends paid up, and Wilkinson earned a nickname that followed him for the rest of his life. They called him Iron Mad, a madman who happened to be completely right. But here's the thing: a barge on a calm river is one situation. A massive vessel out in the open ocean, facing real waves and real storms, is an entirely different beast. It would take almost 60 more years before anyone dared to test iron against the true fury of the sea. That test came in 1843, in Bristol, when an engineer named Isambard Kingdom Brunel launched a ship called the Great Britain. This thing was enormous for its era, 98 meters long, over 1,000 tons of solid iron, and it was designed to actually cross the Atlantic Ocean on a regular schedule, carrying passengers. Newspapers at the time practically guaranteed disaster. They wrote that this iron monster would sink the moment it touched open water, taking every passenger down with it. People gathered at the docks specifically to watch it fail. Instead, they watched 1,000 tons of iron glide calmly out of the harbor and head straight for the open Atlantic. Now, I won't pretend the story has a perfectly clean ending, because the Great Britain actually ran aground later on the coast of Ireland and sat stuck on the rocks for over a year. But here's the part that matters. If that had been a wooden ship in the same situation, the waves would have smashed it into splinters within days. The iron hull survived over a year of relentless pounding, got pulled off the rocks, and went right back into service. That one event changed shipbuilding forever. After that, nobody in the industry was asking, will iron ships sink anymore? The question completely flipped. Now they were asking, why doesn't it sink, and how do we use that knowledge to build them even bigger? And the answer to that question is sitting in a discovery that is over 2,000 years old. You've probably heard the name Archimedes, ancient Greek guy, supposedly figured out something important while sitting in a bathtub. Here's what he actually figured out, and I promise this is simpler than it sounds. Any object placed in water gets pushed upward by a force, and that force is exactly equal to the weight of the water the object pushes out of the way. That's it. That's the whole principle. Push an empty cup down into water and you'll feel it resisting. You trying to pop back up. That resistance is Archimedes' principle doing its job in real time, right in your hands. Now here's where it gets interesting. Steel is roughly 8 times denser than water. So logically, steel should always sink, right? A steel object always weighs more than the water it could possibly displace, except, and this is the whole secret, density isn't just about the material. It's about the material plus everything trapped inside its shape. Try this thought experiment with me. Take a flat sheet of metal and drop it into water. It sinks immediately, no surprise there. Now take that exact same sheet of metal, same weight, same material, and bend it into the shape of a bowl. Drop that in the water instead. It floats, same steel, same weight. Completely different outcome. Why? Because the bowl shape traps air inside it, and when you calculate the average density of that bowl, the steel plus all that trapped air together, the number drops way below the density of water. The steel didn't get lighter. The system got lighter because of what's contained inside the shape. This is exactly what a ship's hull is. It is not a solid block of steel. It is a carefully engineered hollow shape, a giant sealed container filled mostly with air, cargo space, and empty compartments. The steel walls are just the boundary. What's inside those walls is what actually determines whether the whole thing floats or sinks. Simple, right? A kid could understand it once you see the bowl example. But here's a question I want you to sit with for a second. If it's really this simple, just build a big enough hollow shape, then what's actually stopping a storm from just knocking that hollow shape over sideways? Because floating is one problem. Staying upright while the ocean is actively trying to roll you over is a completely different problem. And this is where things get genuinely fascinating. Every ship has something called a metacentric height. I know, that sounds like a boring engineering term you'd hear in a classroom, right? Before falling asleep. But stick with me, because this concept is the actual reason a 6,000-ton tanker doesn't flip over in a storm, and it's honestly one of the coolest pieces of physics in this entire story. Think of one of those inflatable punching bag toys, the kind with the weighted bottom that you punch as hard as you can, and no matter how hard you hit it, it always wobbles back upright. You can't knock it over permanently. Punch it left, it swings, and then it corrects itself. Punch it right, same thing happens. A well-designed ship works on almost exactly that same principle. When a wave tilts the ship to one side, the shape of the hull and the position of its weight create a righting force, a force that actively pushes the ship back toward upright, the same way that punching bag toy corrects itself. Engineers spend enormous amounts of time calculating exactly where the weight sits inside a ship, exactly how the hull shape distributes buoyancy, specifically so that when the ocean punches the ship sideways, physics itself fights back and rights the vessel. Now let's actually talk numbers, because I think you need to see just how extreme this gets in real life. There is a supertanker called the Knock Nevis, built back in 1979 in Japanese shipyards. This is, without exaggeration, the largest ship that has ever existed, 458 meters long. To put that in perspective, that's longer than most skyscrapers are tall, except this thing is lying on its side floating on water, 68 meters wide. When fully loaded, it's at 24 meters deep in the water. That's roughly an 8-story building submerged beneath the surface. It could carry over 560,000 tons of crude oil. Add the weight of the ship itself. The total mass pushing down on the ocean exceeded 600,000 tons. Let that sink in for a second, pun fully intended, 600,000 tons. That is roughly equivalent to the weight of 4 million cars, all held up by nothing but a physics principle discovered in a bathtub over 2,000 years ago. And it's not just cargo ships pulling off this trick. Take the USS Gerald R. Ford, the largest aircraft carrier on the planet, put into service in 2017. 337 meters long, displacing roughly 100,000 tons, on board at any given time around 7,000 crew and air personnel, more than 90 aircraft and helicopters, thousands of tons of jet fuel, ammunition, supplies for months at sea. And here's the part that should really mess with your head. This 100,000-ton steel city can move through the ocean at 30 knots, which is about 56 kilometers per hour. That means an aircraft carrier weighing as much as a small mountain can move faster than plenty of speedboats you've probably ridden on vacation. Two nuclear reactors powering for propeller shafts make that possible. But the reason it stays upright while doing it, the reason storms don't roll a 100,000-ton warship onto its side, that's still the same density and stability principle we've been talking about this entire video. Quick question for you, and I actually want you to think about this before I answer it. If this physics is so reliable, so mathematically proven, why do ships ever sink at all? If Archimedes figured this out over 2,000 years ago and engineers have had centuries to perfect it, shouldn't this problem be completely solved by now? Here's the uncomfortable truth. The physics never fails, not once. What fails is when human decisions, mechanical damage, or freak conditions push a ship past the limits that engineers calculated it could handle. Let me show you exactly what that looks like, because these next two stories are genuinely haunting. April 14, 1912, the North Atlantic. The Titanic is cutting through freezing waters known to be full of icebergs at that time of year. For 1912 standards, this ship was considered extremely well protected. Its hull was divided into 16 separate watertight compartments. Engineers had calculated that the ship would remain afloat even if any 4 of those compartments completely flooded at the same time. That's a massive safety margin. On paper, this ship should have survived almost anything. The iceberg destroyed that calculation in a way that nobody had planned for. Instead of ripping one single massive hole into the side of the ship, which is what everyone had designed around, the impact happened at a shallow angle and caused a series of smaller punctures and deformations spread across 6 compartments simultaneously. 6, not 4. The ship was designed to survive 4. The ocean gave it 6. Water started pouring in slowly, but through 6 different points at once. As the front compartments filled, the bow of the ship began sinking deeper. Water started spilling over the tops of the internal walls into the next compartments, and the next, like an ice cube tray, overflowing one section at a time. Eventually, the back of the ship rose so high out of the water that the steel simply could not support its own weight anymore. The hull tore itself in half. Of the 24 people on board, 720 survived. The rest did not make it out of that freezing water. Here's a genuinely uncomfortable question. Do you think the engineers who designed the Titanic were bad at their jobs? I don't think so. I think they solved for a scenario nobody had considered: a diagonal, spread-out impact instead of one clean puncture. And that single oversight changed maritime law forever. After this disaster, it became mandatory worldwide for watertight compartments to extend all the way up to the top deck instead of stopping partway up like they did on the Titanic. That one rule, born from this exact tragedy, is still in force today, in an updated form, on every large ship you'll ever step foot on. But the Titanic isn't the only lesson the ocean has taught engineers the hard way. September 1994. A ferry called the Estonia is crossing from Tallinn to Stockholm carrying 853 people. A storm hits, with waves reaching for 5 meters. At the front of the ships, it's a massive bow visor. Think of it as a giant steel shield that seals the opening where vehicles drive on and off. That night, this 55-ton steel shield simply could not withstand the repeated pounding of the waves. It broke loose and sank straight to the bottom of the sea. Through that now open hole, water flooded directly onto the vehicle deck within minutes. And here's where something called the free surface effect kicked in, a phenomenon that terrifies naval engineers to this day. When hundreds of tons of water starts sloshing freely across a large open deck, every time the ship tilts even slightly, that water surges toward the low side, adding even more weight to that side, tilting the ship further, which sends even more water rushing that direction. It's a feedback loop. Each tilt makes the next tilt worse. The ship leaned to one side. The water rushed that direction and made it lean further. Within about 20 minutes, the Estonia had completely rolled over and sank. Only 137 of the 853 people on board survived. It remains the deadliest peacetime maritime disaster in European waters since World War II. I want you to notice something these two disasters have in common, because it's the single most important lesson in this entire video. In both cases, the physics never stopped working. Buoyancy didn't fail. Archimedes' principle didn't take the night off. What happened is that real-world damage pushed each ship past the specific limits its engineers had calculated for. The math was right. The conditions exceeded the math. So how do modern engineers respond to knowing that reality? Simple: they stopped designing for the expected worst case and started designing for something significantly beyond it. Modern ship hulls are built to withstand loads 1.5 to 2 times greater than what the ship is realistically expected to face in its entire operational life. That extra steel, that extra strength, costs shipping companies enormous amounts of money, but it's the price they pay so that a shallow iceberg scrape or one broken Bow visor doesn't turn into a headline disaster. Now let's actually address the storm scenario directly, because that's what you clicked on this video to learn about. When a fully loaded oil tanker is caught in genuinely severe weather, the ship isn't just floating there passively hoping for the best. Every large vessel has ballast tank sections deliberately filled with seawater, specifically to control balance and stability. Before heading into rough conditions, crews carefully calculate exactly how much ballast water they need, positioning weight low in the hull to lower the ship's center of gravity. A lower center of gravity means a stronger righting force. Remember that punching bag toy, meaning the ship resists tipping over even more aggressively when waves slam into it. On top of that, modern tankers are built with something called a double hull, essentially a ship built inside another ship, with a gap of empty space between the two layers. If the outer hull gets breached by anything, ice, rocks, even another vessel, the inner hull remains intact and the ship keeps its buoyancy and its cargo contained. This design became mandatory worldwide specifically after major tanker disasters caused catastrophic oil spills. It has genuinely saved both lives and oceans since being implemented. So here's the answer to the question in the title of this video. A massive oil tanker survives a violent storm because of a stack of overlapping safety systems working together, the fundamental shape of the hull trapping enough air to stay buoyant, mathematically calculated center of gravity that actively fights to keep the ship upright, ballast systems that get adjusted specifically for the conditions ahead, and structural steel built to handle stress levels far beyond anything the ship should realistically ever face. None of that is luck. Every single piece of it is deliberate, calculated, and specifically engineered by people who spent their careers studying exactly how the ocean tries to kill ships, so they could build something that refuses to let it. Here's one final number that I think puts this entire video into perspective. Right now, at this very moment, approximately 90% of everything traded across the entire planet is moving across an ocean on a ship just like the ones we've been discussing: your phone, your shoes, the fuel in your car. Almost all of it spent time in the belly of a massive steel hull that stayed afloat, stayed upright, and made it safely to a port, purely because of a physics principle an ancient Greek scientist figured out sitting in his bathtub over 2,000 years ago. The ocean is trying to sink these ships every single day. It genuinely is waves, storms, corrosion, pressure, all of it working constantly against the hull, and every single day, engineering wins that fight. Not because the ocean got weaker, because humans got smarter. So next time you see a photo of some absolutely massive cargo ship or tanker out on the open water, I want you to actually think about everything happening beneath that surface: the hollow-shaped wrapping air exactly where it needs to be, the ballast tanks positioned with mathematical precision, the steel reinforced to handle forces most of us will never even witness in person. It's not magic. It never was. It's just really, really good physics applied by people who refuse to let the ocean win. If this changed the way you'll look at ships forever, you know exactly what to do. Hit subscribe, because we've got plenty more of these stories coming about the massive machines and hidden engineering that quietly run the entire world around you without most people ever noticing. I'll see you in the next one.